It's 6 a.m., and Kevin can barely stand up straight. He grips the edge of the bathroom sink, his knees buckling, the room tilting sideways as if the floor itself is sliding out from under him. 24 hours earlier, he was a healthy 65-year-old retiree, snacking on what he believed was one of the best health decisions he'd made all year. Now, he's staring into the mirror at a stranger, skin drained of color, the whites of his eyes stained a sickly yellow, his urine the color of strong tea. His heart is pounding so hard he can feel it in his throat. He doesn't know it yet, but inside his bloodstream, millions of his own red blood cells are rupturing by the second, releasing toxic waste products that are actively poisoning his kidneys. Within hours, he'll be in an emergency department, hooked up to IV fluids, receiving an emergency blood transfusion, while doctors race to figure out what's attacking his blood from the inside. And the trigger for all of it wasn't a virus, a toxin, or a snake bite. It was a bag of beans. This is the story of a genetic condition called G6PD deficiency, and it's a condition with a surprisingly long history. In fact, the idea that certain beans could be dangerous predates modern medicine by roughly 2,500 years. The ancient Greek philosopher Pythagoras, in the 6th century BC, is famously said to have forbidden his followers from eating fava beans. And for centuries, historians assumed this was some strange mystical dietary rule with no scientific basis. It wasn't until the 20th century that doctors realized Pythagoras may have been onto something real. In the 1950s, researchers studying American soldiers given a new anti-malarial drug called Primakene noticed something bizarre. A subset of soldiers, disproportionately those of Mediterranean, African, and Asian descent, developed sudden severe anemia after taking the medication, while everyone else tolerated it just fine. By 1956, scientists had traced the cause to a missing enzyme in the red blood cells of the affected soldiers, an enzyme called glucose-6-phosphate dehydrogenase, or G6PD for short. And it didn't take long for researchers to connect the dots back to that ancient Greek taboo. The condition that made certain people react violently to Primakene was the very same condition that, in some people, causes a dangerous reaction to fava beans, a phenomenon now formally known as favism. Pythagoras, it turns out, may have simply been observing a pattern that took modern science another 2.5 millennia to fully explain. Now, let's go back to Kevin. He's 65, recently retired, and determined to finally get serious about his health. He'd always been a chronic snacker, the kind of guy who never went more than an hour without a bag of chips or pretzels within arm's reach. So when a friend recommended puffed bean snacks, plant-based, high in protein and fiber, marketed as a smarter alternative to processed junk food, Kevin was sold. He tried them, loved them, and before he realized it, he had polished off 3 entire bags in one sitting. He felt a little bloated afterward, but nothing that seemed remotely alarming. The next morning, though, Kevin woke up feeling like he had a brutal hangover. He was exhausted, his head throbbed, and a wave of nausea hit him before he'd even gotten out of bed. He also noticed a strange, dull ache low on the right side of his abdomen. He chalked it up to the salt content in the snacks and started drinking water to flush it out of his system. But instead of improving, the pain and nausea only got worse throughout the day, and his appetite vanished completely. By the following morning, Kevin felt genuinely awful. His skin felt hot and prickly, like he was running a fever, and when he finally worked up the energy to get out of bed, he nearly blacked out from the head rush. He stumbled into the bathroom and froze. His urine had turned dark brown, almost the color of cola. And when he looked up into the mirror, panic set in. Staring back at him was a pale, almost ghostly version of himself, and the whites of his eyes had turned a deep, unmistakable yellow. His heart was racing uncontrollably. He called his neighbor, who rushed him straight to the nearest emergency department. When a patient arrives in the emergency department, the first person they typically see is a triage nurse who takes a rapid history, checks vital signs, and determines how urgently the patient needs to be seen by a physician. In Kevin's case, 3 specific findings immediately caught the triage team's attention: fever, pain in the right upper portion of his abdomen, and jaundice, the yellowing of the skin and eyes. His heart was racing uncontrollably. He called his neighbor, who rushed him straight to the nearest emergency department. Together, these 3 findings form what's known in medicine as Charcot's triad. And it's a combination that can never be ignored, because it classically points toward a life-threatening infection of the bile ducts called acute cholangitis. Given the fever and the visible signs of organ distress, Kevin's overall presentation was concerning for sepsis, a dangerous, potentially fatal, whole-body reaction to infection. So the medical team's first priority was stabilization, starting him immediately on IV fluids and powerful broad-spectrum antibiotics. This is one of the foundational principles of emergency medicine. Stabilize the patient first, and simultaneously work through the most dangerous, life-threatening possibilities before moving on to rarer explanations. Kevin was sent for an urgent abdominal ultrasound to check for the blocked or infected bile ducts that would confirm cholangitis. But the results came back reassuring. His bile ducts appeared completely normal, and his blood work didn't match the pattern expected in acute cholangitis either. That diagnosis could be crossed off the list, which meant the real cause of Kevin's crisis was still hiding somewhere else in his body. So the team turned to his initial blood work, and a few numbers immediately stood out. His hemoglobin was low, meaning he was significantly anemic. His LDH, a protein released into the bloodstream whenever tissue or cells are damaged and breaking down, was strikingly elevated. And his total bilirubin level was extremely high. That explained the yellow tint in his eyes, since bilirubin is the yellow-orange pigment produced when the hemoglobin inside red blood cells gets broken down. But there was a second, more revealing test buried in that blood work: direct bilirubin, which measures specifically how much of that total bilirubin the liver has already processed and prepared for elimination from the body. In Kevin's C. In Kevin's case, that number was disproportionately low compared to his sky-high total bilirubin. And this discrepancy is where the case takes its most important turn. Put all of these findings together, and they tell a very specific story. Kevin's red blood cells were bursting open at an alarming rate, spilling both LDH and hemoglobin directly into his bloodstream. That liberated hemoglobin was rapidly being converted into massive quantities of bilirubin, but the sheer volume overwhelmed his liver's normal capacity to process and clear it, so it backed up in his bloodstream, staining his eyes and skin yellow. This entire process has a name: acute hemolysis, derived from the Greek roots for blood and breaking apart, describing the destruction of red blood cells faster than the body can replace them. Now, the real detective work began because knowing what was happening didn't yet explain why. Physicians generally divide the causes of hemolysis into two broad categories. The first is external factors, things from outside the red blood cell that attack and destroy it, which can range from the immune system mistakenly targeting its own blood cells, to mechanical damage caused by a malfunctioning or artificial heart valve shredding cells as they pass through, to certain infections and toxins. The second category is internal factors, structural weaknesses built into the red blood cells themselves that make them inherently fragile and prone to rupturing under stress, the most well-known example being sickle cell disease. Tests were ordered to screen for conditions in both categories, but lab results take time, and Kevin's condition was rapidly deteriorating in the meantime. His hemoglobin kept dropping hour by hour, and he ultimately required an emergency blood transfusion just to stabilize him. Then more bad news arrived. Despite aggressive IV fluid resuscitation, his kidney function was actively worsening. This makes physiological sense because the free hemoglobin flooding out of ruptured red blood cells is directly toxic to kidney tissue. And as it filters through into the urine, it's exactly what was turning Kevin's urine that alarming dark brown color. At this point, saving his kidneys depended entirely on identifying the underlying cause of the hemolysis quickly enough to stop it. So the team went back through the differential diagnosis, systematically ruling things out. His platelet count and coagulation testing came back completely normal, arguing against a clotting disorder shredding his red blood cells. His ultrasound showed a normal-sized spleen, arguing against certain inherited blood disorders and some autoimmune conditions. The team confirmed he hadn't traveled recently, had no contact with exotic animals, no snake or insect bites, and hadn't started any new medications, ruling out several toxic and infectious causes. One by one, the obvious explanations fell away. It was ultimately Kevin's blood smear, a sample of his blood examined directly under a microscope, that provided the breakthrough. Under magnification, technicians noticed something unusual: red blood cells that looked as though a small semicircular bite had been taken directly out of them. In hematology, these are literally called bite cells, alongside a related finding called blister cells, cells with a thin, bubble-like blister forming on their membrane. Using a specialized stain, the lab uncovered the deeper explanation. Many of these damaged cells contained small, dark clumps sitting just inside the cell membrane, structures known as Heinz bodies, which are essentially wads of denatured, damaged hemoglobin that is clumped together and stuck to the inside of the cell wall. As these damaged cells circulate through the spleen, the macrophages stationed there, cells whose entire job is to inspect passing blood cells and destroy anything abnormal, recognize these clumps as a defect and quite literally bite a chunk out of the red blood cell to remove the damaged material, leaving behind those telltale bite and blister cells. This finding pointed the team toward a very specific category of disease, a structural problem with Kevin's hemoglobin itself, which strongly suggested a genetic cause. And that raised an obvious question. If this was genetic, Why was a 65-year-old man only now discovering it? Kevin's doctor went back and dug deeper into his family history, and a pattern started to emerge. It turned out that Kevin's maternal grandfather had suffered from unexplained recurring episodes of jaundice and anemia throughout his entire life, but had lived and died decades earlier without ever receiving a formal diagnosis, in an era when this kind of enzyme testing simply didn't exist. Then Kevin's doctor asked what seemed like an oddly specific, almost random question. Had he eaten any fava beans recently? Kevin reached into his bag, pulled out the empty snack packaging, and there it was, printed clearly on the ingredient list: fava beans. With that single piece of information, combined with everything else, the diagnosis became almost certain. Kevin had G6PD deficiency. So what exactly is G6PD, and why would an enzyme deficiency turn a bag of bean snacks into a medical emergency? G6PD stands for glucose-6-phosphate dehydrogenase, and it's a critically important protective enzyme found inside every cell in your body. To understand why it matters, you have to understand a strange paradox about oxygen itself. Oxygen is essential for keeping every cell in your body alive and functioning, but it's also inherently dangerous because the process of using oxygen generates unstable reactive molecules that can damage cells from the inside, a phenomenon called oxidative stress. To survive this constant low-grade bombardment, your cells evolve defense systems built around antioxidants, molecules that neutralize these reactive byproducts before they can cause harm. Think of it like a sci-fi analogy. Oxidative stress is the incoming laser fire, and antioxidants are your ship's shields. Every cell in your body contains G6PD, and its job is to help manufacture and continuously regenerate one of the body's most important antioxidant molecules, called glutathione, or GSH. The more functional G6PD you have, the stronger and faster regenerating that antioxidant shield becomes. But if you're significantly deficient in G6PD, that shield can be knocked out far more easily, leaving your cells, and particularly your red blood cells, dangerously exposed to oxidative damage. But what does any of this actually have to do with beans? Fava beans contain naturally occurring compounds, including vicine and convicine, which get metabolized by gut bacteria into chemicals capable of generating a sudden, intense surge of oxidative stress. In someone with normal G6PD levels, this surge is easily neutralized and barely registers. But in someone with G6PD deficiency, that antioxidant shield simply can't keep up, and the resulting oxidative damage overwhelms and ruptures red blood cells on a massive scale, triggering the destructive cascade doctors now call favism. Red blood cells are uniquely vulnerable to this particular kind of attack because, unlike most other cells in the body, they lack a nucleus and the backup cellular machinery that other cell types can call upon when their primary antioxidant defenses fail. For red blood cells, G6PD isn't just one defense system among several, it's essentially the only meaningful line of defense they have, which is exactly why this deficiency devastates red blood cells specifically, while leaving most other tissues in the body largely unaffected. Remarkably, G6PD deficiency is one of the most common inherited enzyme disorders in the world, affecting an estimated 400 million people globally, and roughly 2% of the entire population of the United States. It's especially prevalent among people whose ancestry traces back to regions historically hit hardest by malaria, including parts of Africa, the Mediterranean, the Middle East, and Southeast Asia. And that geographic overlap is not a coincidence. Malaria is caused by a parasite that must invade and hijack red blood cells in order to reproduce and spread throughout the body. Inside a normal, healthy red blood cell, the malaria parasite can effectively hide, replicate undisturbed, and shield itself from much of the body's immune response. But inside a G6PD deficient red blood cell, the additional oxidative burden created by the parasite's presence pushes that already fragile cell over the edge, damaging its membrane and causing the body's surveillance systems to detect and destroy the infected cell before the parasite has a chance to fully mature and spread. In other words, people with G6PD deficiency can still contract malaria, but they tend to experience less severe disease and have meaningfully better odds of survival, which is very likely why the genetic mutations responsible for G6PD deficiency have persisted and even become common across generations in regions where malaria has historically posed a major threat to survival. It's a striking example of evolutionary trade-off, a genetic quirk that carries real risk in one specific context, like eating fava beans or taking certain medications, while offering a meaningful survival advantage against one of history's deadliest diseases. This still leaves an important question. If G6PD deficiency is something you're born with, how could Kevin have lived a full 65 years without ever knowing he had it? The answer is that G6PD deficiency exists across a wide spectrum of severity, driven by exactly which genetic variant a person carries. At the most severe end of that spectrum, people experience chronic hemolysis, meaning their red blood cells are breaking down persistently, even under the ordinary, everyday oxidative stress that everyone's cells experience simply from normal metabolism, without any unusual trigger required at all. But at the milder end of the spectrum, where Kevin fell, a person's baseline enzyme activity is reduced, but still functional enough to handle normal daily life without issue. It typically takes a substantial concentrated trigger, in Kevin's case, binging through 3 entire bags of fava bean snacks in a single sitting, to overwhelm that reduced but otherwise adequate antioxidant defense and provoke a full-blown hemolytic episode. With that, Kevin's entire ordeal finally made complete sense from start to finish. He had been living with undiagnosed mild G6PD deficiency for his entire life, quite possibly experiencing minor unnoticed episodes over the decades that were never severe enough to prompt a trip to the doctor. But after consuming bag after bag of fava bean snacks, his red blood cells began rupturing en masse. As hemoglobin spilled out of those disintegrating cells, it began mopping up nitric oxide circulating in his bloodstream, a molecule that normally helps keep smooth muscle relaxed, and the resulting depletion caused smooth muscle in his gut to constrict, producing his abdominal pain and nausea. The same destructive process also triggered a surge of systemic inflammation, prompting his body to mount a fever response, even though there was no actual infection driving it. When he stood up and nearly blacked out, that was a classic symptom of severe anemia. His brain simply wasn't receiving enough oxygen-carrying blood to function normally in an upright position. Meanwhile, the enormous surge of hemoglobin being broken down was converted into more bilirubin than his liver could keep pace with, turning his eyes and skin yellow, while the free hemoglobin that spilled directly into his urine gave it that dark, tea-colored appearance and, critically, began actively damaging his kidneys along the way. Fortunately, after several days on aggressive IV fluid support in the hospital, the oxidative compounds from the fava beans were fully cleared from his system. His red blood cells stopped rupturing, his urine gradually returned to its normal color, and his kidneys made a complete recovery. His liver finally caught up on processing the backlog of bilirubin, and the yellow tint drained from his skin and eyes. From that point forward, Kevin became meticulously careful about avoiding known triggers, steering clear of fava beans entirely and checking with his doctor before starting certain classes of antibiotics and other medications known to provoke hemolysis in G6PD deficient patients, including some antimalarial drugs and specific pain relievers. After hearing a story like this, it would be reasonable to wonder why anyone would willingly eat fava beans at all, given the oxidative stress they can trigger. But the relationship between the body and oxidative stress isn't nearly as simple as good versus bad. Physical exercise, for instance, also generates meaningful oxidative stress in the body, and yet it's unquestionably one of the healthiest things a person can do, because the body adapts and strengthens its defenses in response. Some researchers even believe that small, controlled pulses of oxidative stress may help train and reinforce the body's natural antioxidant defense systems over time, a concept sometimes referred to as hormesis. So for the vast majority of people, those with normal G6PD activity, fava beans and puffed fava bean snacks remain a perfectly reasonable, nutritious food to enjoy in moderation, offering solid plant-based protein and fiber without any risk at all. The danger is specifically, and almost exclusively, confined to that roughly 400 million people worldwide who carry a deficiency in this one particular enzyme, many of whom, like Kevin, have absolutely no idea they're carrying it until the day their body meets the wrong trigger at the wrong dose. That's precisely what makes G6PD deficiency such a striking medical story. A mutation older than written history, first hinted at by a philosopher's dietary warning 25 centuries ago, still quietly shaping how hundreds of millions of people's bodies respond to something as ordinary as a bag of beans, right up to the present day.